Everyone, welcome to today's lecture. So today we're still on thermodynamics and we're still on thermophysics. My name is Harmtedy. So this is lecture 2, and today, to be specific, we'll be looking at the anomalous behavior of water and the ideal gas laws and the other laws. Okay, so this is what I'm just talking about. We'll look at the anomalous behavior of water at 4 degrees below and above 4 degrees. And then we'll also discuss the ideal gas laws. Okay, so we know to say when you heat or when you increase the temperature of every substance, it begins to expand, of most substances. But for water, this is not the case. For water, when you increase its temperature from 0 degrees, if you have, this is a table, if you have something like this, 1 2 3 4 5 6 7, 1 2 3 4 5 6 7. So for water, as you begin to increase the temperature, this is the temperature in degrees Celsius, and then we have the volume this side in cubic centimeters. So as you increase the temperature of water from 0 degrees going up, the volume begins to reduce, and then the minimum volume is usually at 4 degrees. Yeah, so the minimum volume is usually at 4 degrees. From there, it will begin to increase, to begin to behave like other substances. Yeah, so this is not the case when you are dealing with density, because we know to say density is equal to mass over volume, and then from this you can just tell to say density is inversely related to the volume. So meaning while the volume is increasing, the density will be reducing. When you increase the volume there, the density begins to reduce. So if you are to sketch the graph there of the density in kg per meter cubed, again, towards is to the temperature in degrees Celsius, you discover that you have a graph which will be somehow like this. And then from there, at this point, this is the point at the turning point here of the curve. That is where our 4 degrees is, 4 degrees Celsius. And then this is where our maximum density is, which is 1 cubic centimeters. Okay, so let's just look at these few notes here. So most substances expand more or less uniformly with an increase in temperature, as long as there is no phase change, as long as there is no phase change. Water, however, does not follow the usual pattern. So this is what I'm just from explaining. Water behaves abnormally, in short. It doesn't behave the normal way, the way other substances behave. Yeah, for water, it will first reduce in volume, and then at 4 degrees, that's when it will begin to increase in volume. Okay, so this is what this point is also talking about. Yeah, so let's quickly look at the table. Okay, this is what everything is just talking about. Okay, so when you look at the table here, this is what I'm also from just talking about. This is for the volume. This is for the volume, and then this is for the density. We know to say as you increase the temperature in degrees Celsius, at 4 degrees Celsius, the volume is minimum. Yeah, the volume is minimum for water. Yeah, so as you increase the temperature, the density is maximum, which is equivalent just to 1 there at 4 degrees. Okay, so as you increase the temperature, the density also increases up to 4 degrees, and then from 4 degrees it begins to reduce. So this is what I just talked about in the first slide there. Okay, so let's quickly move on. So let's look at the gas laws. Yeah, so the gas laws, before we talk about the gas laws, we need first to talk about the so before we talk about the gas laws, we need first to talk about an ideal gas. We need to know what an ideal gas and its properties. So an ideal gas is just a hypothetical gas. It's just a theoretical gas, sorry. That is just an imaginary gas, which it's just an imaginary gas which is used for assumptions in the labs and uh, when doing experiments. Yeah, so we imagine that every gas that we deal with in the lab is an ideal gas. That's why we use the ideal gas laws. Okay, so what you need to know and understand about an ideal gas is that its particles are very much smaller and assumed that they don't interact, they don't collide in short. And then they are also assumed to say the I don't know there is just a distance between these particles. Yeah. Okay. Let's look at the properties by the way. So the gas molecules are very much small. This is the first property. And then the second property here, the gas molecules have very weak intermolecular forces. The gas molecules are very hot, so they move quickly around and don't interact with each other much. And then the gas is at low pressure, so the molecules have a lot of space between them. Okay, so let's move on. Okay, so let's look at the gas laws. Okay, so the gas laws, we all know them. These are the laws that we've also learned from high school. This is we have Bose's law, we have Charles' law, we also have Gay-Lussac's law. So Bose's law. So when you talk about Bose's law, Bose's law simply considers the temperature to be constant. So when you're talking about Bose's law, you have to consider T to be constant, meaning you're just dealing with other meaning you're just dealing with the pressure and the volume. So Bose's law states that the pressure is inversely proportional to the volume. Rather, the volume is inversely proportional to the pressure. It's still the same. So this can also be written as P. Okay, this one is only valid when temperature is kept. So when temperature is kept constant. Yeah, so this one is only valid when temperature is kept constant. And then this can also be written as PV is equal to K. Okay, so in terms of sketching the graph, some are going to be like this. Here we're saying as the pressure is increasing, the volume reduces, or as the volume is increasing, the pressure reduces. So as we increase the pressure, as we increase the volume, the pressure reduces. So we have, this is the volume, then this is the pressure. So as we increase the volume, the pressure reduces. So this is what you're going to have as your curve. Okay, let's take a look at. Okay, so when the gas is kept at constant temperature, the pressure is inversely proportional to its volume. So that is Bose's law. Yeah, so this is what I just sketched, then that is what I was just discussing. So let us also look at Charles' law. We look at Charles' law. Charles' law states that when the pressure of a gas is kept constant. So when dealing with Charles' law, you consider the pressure to be constant, meaning the volume will be directly proportional to its temperature. So you can write this as V is equal to KT, meaning V over T will just be equal to K. Yeah, so this can also be written as V1 over T1 is equal to V2 over T2. This is Charles' law. Yeah, so this is basically what it means. And then when it comes to sketching, it means that you're just going to have a straight line. As you increase the temperature, the volume will also increase. So when you're increasing the temperature this side in degrees, the volume will also be increasing. This side the volume is in cubic meters. Okay, so this is basically what I'm talking about. So let's also look at the Gay-Lussac's law. So this one states that when you keep the volume constant, the pressure, when you keep the volume constant, as long as you keep the volume constant, the volume of that gas, the pressure will be directly proportional to the temperature. So this can, in a similar way, be written as P is equal to KT. So from there, you can say P over T is equal to K, which can also be written as P1 over T1 is equal to P2 over T2. Yeah, so this is Gay-Lussac's law. Okay, so when you combine the three laws that we've learned, you come up with this. So after combining the three laws, you have this as a result. So this is a very important equation which you need to know. Of course, P is the initial pressure, V1 is the initial pressure, initial volume, P2 is the final volume, V2 is the final P2 is the final pressure, V2 is the final volume, then T2 is the final temperature, T1 is the initial temperature, and of course these temperatures are supposed to be in Kelvin. Okay, so this is just a summary of the four laws that we've discussed. We have the Bose law, Charles' law, Gay-Lussac's law, and you also have the combined gas law. Okay, even this one here is just a summary of the laws, except that it has the ideal gas law down there. Okay, let us now discuss this same ideal gas law. So the ideal gas law comes from the same three laws that we've just discussed. We know to say the volume of a gas at constant temperature is directly proportional to is inversely proportional to the to its pressure. This is Bose's law. And then we also have Charles' law, which states that at constant we also have Charles' law, which states that at constant pressure, as long as the pressure is kept constant, the volume of a gas is directly proportional to its temperature. So this is Charles' law. Then there's also the Avogadro's law. So the Avogadro's law states that the volume, or rather when you increase the volume of a gas, its number of moles also increases, meaning the volume is directly proportional to the number of moles. So when you increase the number of moles, the volume also increases of that particular gas. Okay, so this one is the Avogadro's law. So when you combine the three laws, you come up with what is called the ideal gas law. So this side will only have V. So on this side we'll only have V, because there are only V's this side. And then this side will have, this will be directly, so meaning V is directly proportional to N and then T, then over P. So V will be direct proportional to NT and inversely proportional to P. So now the constant of proportionality, if we change this if we change this proportionality symbol to an equal sign, we have to introduce the constant of proportionality there. So V will now be equal to N. This constant of proportionality, we're going to call it R, and then T there, and then everything divided by P. So this R is just called the gas constant. So we can now write this equation as, when you cross multiply there, you have PV is equal to nRT. Of course, the N here stands for the number of moles of that given gas, and then R is just the gas constant of that given gas. Temperature is just, T is just the temperature in Kelvin. Then the pressure there, we know the pressure, and the volume is just volume, we know it. Okay, so let's quickly take a look at this gas constant, ideal gas law. So this is what I've just derived. Yeah, the pressure there, the nRT there in the volume. Okay, so let's take a look at this example here, which talks about how to use the same ideal gas law. So the question says an ideal gas at 20 degrees Celsius and a pressure of 1.5. This was supposed to be 1.5 times 10, or 1.503 times 10. Let me write it properly. So supposed to be 1.503 times 10 to the power 5 pascals. And then from there it continues and says in a container having the volume of 1 liter, determine the number of moles of the gas in the container. So this one is straightforward. We know that the ideal gas law states that the volume, and the pressure times the volume, is just equal to the number of moles times the gas constant R times the temperature in Kelvin. So we just have to make N the subject of the formula, which is the number of moles, because the first question there is asking us to determine the number of moles of a gas in the container. So N will be equal to the pressure times the volume over the gas constant times temperature. So here it's just a matter of plugging in the values and then you do the calculations. But of course, before you even start doing the calculation, you make sure that you convert this temperature to Kelvin. So we know that the conversion factor for, or the conversion equation for the temperature in degrees to Kelvin is simply just T is equal to the temperature in degrees Celsius plus 273.15. So to convert this, we're going to say 20 plus 273.15. Then when you add the 2, you just get 293.15. So this is the temperature that you are going to use at T there. Then R is normally given if it's in an exam. If it's in class, you just have to use a book, any physics textbook. It has a table which consists of the gas constant. Yeah, so you'll find it there. So R is sometimes 8.31. You can either use this one depending with the units that you've been given for pressure. So joules, and then per mole Kelvin, and then there's also this one 0.0821. This is in liters, atmosphere, and then mole Kelvin. So this is what you have. these are the two values of R that you can use. There are also other values of R depending on the pressure that you've been given, but they're just the same. It's just that they've been converted into different units. Yeah, so according to this question here, we're going to use this one because the pressure is in pascals. So you put your pressure there, so you're going to have N is equal to, the pressure that we've been given is 1.503 times 10 to the power 5. You write it there, so okay, 1 point, okay, so you write it there, and then from there you multiply it with a volume there. You convert that volume to you convert this volume to cubic meters. Okay, so this is not difficult. Convert that volume to cubic meters, and then you write your gas constant there, which is there. And then you also write your temperature 293 there, and then you use the calculator to calculate and find your answer. So after doing the calculations, you find your answer to be that. This is the answer that you're going to find, 6.16 times 10 to the power negative 2 mole. Okay, so let's quickly move on to the next one, which is B. The gas pushes against a piston, expanding to twice its original volume, while the pressure falls to atmospheric pressure. Find the final temperature. So this one, once you hear about a final temperature, it means that there's also supposed to be an initial temperature somewhere. And the only formula that consists of the initial and the final temperature is simply just P1 V1 over T1 is equal to P2 V2 over T2. So if you want, yes, that is if you want, you can use this one. But you can also go by the ideal gas law, where you say, you know that PV1 is equal to nRT1. You also say P2V2 is equal to nRT2. So when you divide this over that, even that over that, you discover that this and that will cancel. You just remain with PV11, P2V2 is equal to T1, and then T2 down there. So from there now you can just make they're asking us to find the final temperature. You can just make the final temperature according to your assumptions there. If T2 was your final temperature, you can make T2 the subject of the formula, and then you plug in all the values. Of course you have T1 there, then T2 is the one that you've been asked to find. You have P1, you have V1, you have P2. So P2, they are saying that the pressure dropped, it fell to atmospheric pressure. So atmospheric pressure, you can use, I think it should be 1.01 times 10 to the power 5 pascals. And then they are also, to find V2, they are also saying expanding to twice its original volume. So the initial volume is just 1. So the original volume, which is the initial volume, is 1. But they are saying it expanded to twice its original volume, meaning the final volume becomes 2 times that, which becomes 2 liters. So this is what I'm just trying to talk about. So these are the solutions. This is what I was just trying to talk about. Okay, so let's quickly, I think this is the last slide. Yeah, so thank you very much for watching today's lecture. I'm going to send an exercise which you will be required to submit before Monday, because Monday, that's when we're having our next physics lecture. So make sure that you submit the exercise before Monday. See you in the next lecture for mathematics, and we're starting a new topic in mathematics. So make sure that you attend. You shouldn't be missing first lectures. See you in mathematics tomorrow. Make sure that you subscribe to the channel in case you have not yet subscribed. Okay.